A couple quick basic principles that apply to this. We've already talked in this class about normalization, the idea that you have some probability, you sum it over all possible values of that variable. Probabilities, by definition, has to sum to 1. Normalization. Nothing sophisticated about that. But I think you can see that it immediately starts to give you some interesting operations. For example, the operation of projection, basically a multi-dimensional probability distribution. You want to project it onto a lower dimensional space. In other words, let's say we want to eliminate one of our variables, like x or y. So if we sum over all possible values of x, what are we going to get? Well, we can expand this joint probability clearly in terms of the product, the conditional probability of x given y, unconditional probability of y. This term has no dependence upon the variable that we're summing over, so it factors out of the summation. What's this? This is normalization. It's got to sum to 1, so that all vanishes. And we've just projected down the so-called marginal probability, or unconditional probability of our remaining variables. The term marginal probability is sometimes used for this, going back to the days when people would write probability tables on a piece of paper, and then in the margin, you'd sum all the probabilities in a given row, and you get the unconditional probability of your remaining variable. It's sometimes referred to as a marginal probability, which just means an unconditional probability. Question?
How did you get that center portion?
So all I did was I just said, this is a joint probability, so I can write it as a conditional probability times an unconditional probability. So if you just take this parenthesis out over here, that's the step. And then all I did was I recognized, oh, this doesn't depend on the variable that I'm summing over. This term is not dependent, so I can factor it out of the summation. And then that just sums to 1. So very simple concept, but actually really useful tool. I mean, again and again and again, what you're going to see in statistical inference problems is models that involve variables whose values we have no way of obtaining. Not a problem under this basic formalism. What we can do is we can have models that use those variables, and then we can get rid of them by summing the model over all possible values of such a nuisance variable, and have a rigorous probabilistic analysis that takes into account that variable and all its possible values, but without making any assumptions. Oh, it has to equal 7. Well, how do you know it's 7? It might be something else. This way we're going to get an estimate of the things that we're actually interested in that's properly weighted by all the possible contributions from our nuisance variable, correctly estimated from the model. Any questions about these basic principles?